All right, thank you guys for coming. As Adrian mentioned, I'm a computer vision engineer at a startup called Orbital Insight. We're down in Palo Alto. Oh, and no. All right. So I'm going to start the talk by telling you a little bit about what we do. Hopefully that will give you context for the rest of the talk. And then I plan to spend a little bit of time talking about satellite imagery in general, what's interesting about it, what's unique about it, because I figured that would be new to most of the audience. And then I'll talk about how and why we use deep learning at Orbital Insight and some practical things that we found to be useful, kind of software engineering kind of things. All right, so Orbital Insight, we take geospatial data, primarily satellite imagery, and we use a combination of computer vision, machine learning, deep learning. Those are all kind of interchangeable at this point. Statistical modeling, data science, to turn that data into a big picture understanding of the world. So we want to track economic and environmental trends. So to me, one of the most exciting things about what we do is the fact that we sit at the intersection of two areas that have been going through a lot of rapid progress in the last several years. So one of them is what I call machine intelligence, because I'm embarrassed to use artificial intelligence. So most of you guys are probably familiar with the change that's been happening in that field, mostly the deep learning stuff, right? But I figured some of you might not know the second piece, which is commercialization of space. So I want to tell you a little bit about that. So what's new in the space industry? Well, one thing is rockets have been getting cheaper thanks to private companies like SpaceX. Hardware has been getting better. So we all have one of these in our pockets. It has a pretty good camera. It has a GPS. It has a radio. So if you duct tape a solar panel onto it and you throw it into space, you almost have a satellite, right? Almost. And then the other interesting thing that's been happening is looser regulation. So I had no idea. When you think about the space industry, you think about like the 70s or the 80s, right? And so I kind of naively thought that companies have been operating satellites and selling imagery since the 70s or since the 80s. It turns out it was only in 1992 that this was allowed by the US government. And even then, they actually regulate, there are laws about what resolution you can sell. And for a long time, that was 50 centimeters. It's only in 2014 that they relaxed it down to 25 centimeters. So if you're a company and you have a satellite, you can actually take 30 centimeter imagery. You had to downsample it to 50 centimeters before selling it, which is kind of interesting. So traditionally, satellites for remote sensing, the ones that can take pictures and send them down, they were big, or they are big, very expensive to make, and very expensive to launch into space. The good news is the technology, it's pretty fascinating. You can get 30 centimeter resolution imagery. So you can go to Digital Globe and buy 30 centimeter imagery. And these things are like 300 miles above the ground. So it's kind of crazy to think about that. But the fact that they're so big and so expensive means there's only a handful of them. And what that means is that if you're interested in a particular spot on Earth, the revisit time is not great. You might have to wait a week. You might have to wait a month. The reason it's variable is because some of them have cameras that can actually move, and so they're not. It's not a regular frequency. So one thing that's been happening, though, in the last several years is this emergence of the CubeSat or the small sat idea. So these satellites are much smaller. They're the size of a shoebox. They're way cheaper to construct. This kind of goes back to the better hardware bit on the previous slide. And they're much cheaper to send up. You can actually send up several at a time, and you can piggyback on another launch. You don't need a dedicated rocket anymore. And because these are so much cheaper to send up, you can send up a lot. And so that revisit issue is a lot better now. And is going to get better and better. The only downside is the resolution. There's a physical limit to the resolution just because these things are smaller and the lens is smaller. So the typical resolution you'll get something like 3 meters or 10 meters. So there's a startup in San Francisco called Planet Labs. I don't know if you guys have heard of them. So they're one of the companies that are launching a large constellation of these CubeSats. And Their plan, I guess you probably don't see it, but they have a little widget on their website where you can see kind of what their planned launches are. And this year, they plan on having enough satellites in space to get a revisit rate of 1 to 3 days for every spot on the planet. So they're going to have a picture of the entire land mass of Earth, a fresh one, every couple of days, which is unprecedented. It's pretty crazy. The other plot that I'm showing here is in blue are CubeSats that have already launched, and in red is what companies are planning to launch, and each bar is a different company. So that kind of gives you a sense that this is only the beginning. So a couple of years from now, things are going to look pretty different. So a good pause here. This is great news in a way, right? We have all this data that's about to be streamed down. But traditionally, the way satellite imagery has been consumed is human eyeballs. So you hire an analyst, and they sit in front of a computer, and they look at a particular place. And that was manageable for a while because you only get an image every week or so. But once you have this much imagery getting beamed down, it's really not scalable to do that anymore. And so that's why that intersection of machine intelligence and satellite imagery makes sense. So I'll tell you guys about a couple actual products that we're working on, or a couple applications that we're working on. The most mature product that we have is to do retail forecasting. So we trained a car detector. It's a convolutional neural net. I'll talk about that a little bit later. And we can count cars in parking lots of major retailers. So think stores like Walmart, Home Depot, and so on. And the number of cars is kind of a proxy for revenue, right? The more people that are shopping at the store, the more money they're making. And if you look at one parking lot, again, in part because of the temporal frequency issue, these are high resolution images at 50 centimeters. Otherwise, you can't see the cars. So if you look at just one parking lot, you're not going to be able to say much, right? Cars come and go, and the imagery is not frequent enough. But if you look at this at scale, and again, once you have an algorithm to do this, you don't have to hire people to sit and click on cars. That's when the interesting trends begin to emerge. So to give you a sense of the scale here, we've counted so far 1.2 billion cars in the United States. We're only doing this for the United States right now. And there's like, what, 300 million people in the United States, probably fewer cars than that. So we've counted many cars more than once. So what does the data look like? This is for coals. So you could look at different time windows. If you look at an entire year, you'll see, not surprisingly, a big spike during Christmas, and then after New Year, it kind of falls off for a little bit. If you keep zooming in, you see this crazy outlier, which is Black Friday. And then if you zoom in to days of the week, you see something interesting. So there's a spike on Saturday, which makes sense. There's also a spike on Wednesday. And we actually thought that was a bug for a while. And it turns out that Kohl's has a senior discount day on Wednesday. So that's actually a real phenomenon. We can see that just by counting cars in parking lots. Okay, this is a fun one. So this is a restaurant chain, and you can see they were doing really well 2010 through 2015. They were doing really well, growing for a while, and then things went south. Can you guys guess which restaurant chain this is? Chipotle. That's right. This breaks my heart because I love Chipotle. But yeah, the beginning of all their outbreak problems, that's kind of when things went south. So you can imagine if you're an investor and you're thinking about investing, or you have a position in Chipotle and these things start to come out in the news, you don't want to wait until the quarterly earnings report to find out what the consumer reaction is. And we can see this in more or less real time. So that's the power of this data. So we need more cars there are at that spot compared to the starting position. You can see it really lights up because the city has been going through a lot of development. And you can actually see there's a little suburb that pops into existence. And this is all just from counting cars. Right, so it tells you a lot. Another big thing that we're working on is oil. Oil's been in the news a lot lately. It's a very volatile market. Oil is stored in containers around the world. And it turns out no one has a great idea of what the inventory is, how much oil is sitting in all of the containers all around the world. But luckily, turns out crude oil is stored in these cylindrical containers, and they have a floating lid. So the lid floats on top of the oil. So as you take oil out, the lid goes down. As you put oil in, the lid goes up. And these things are pretty huge, and you can see them very clearly from space. So I'm going to show you a GIF. It's a little bit dizzying, so you might need to look away. The reason it's dizzying is because the viewpoints change, but that's a single tank, and hopefully you can see, there's a lot of stuff going on here, but hopefully you can see that the lid is going up and down. I guess it only plays it once. The other thing that's changing is the sun angle changes, the time of day changes, and that affects the shadow. And those shadows are very informative because we know where the sun is. If we can figure out where the shadow is, we can figure out how full the tank is. And we can do this, again, at scale. We can do this for every tank in the world and get an idea of the oil inventory globally. All right, the last one I'll mention is a water detector. So water is another really important resource, both from an environmental perspective, but it can also affect politics as well. So Landsat, which is a program run by the USGS, they have 2 satellites. It's a government-run program. So if you get their imagery, they actually have a mask. They have a few things. They have like clouds and water and snow and some other things. And I'm not sure what algorithm they're using, but it's pretty hit or miss. I'm guessing that they're using kind of a more traditional approach where they're doing like random forests, and they're looking at a pixel at a time. And sometimes it works fine, and sometimes it just completely drops out. So the blue in this column, in the middle column, is what Landsat says is water. So it's pretty much unusable. So we train a convolutional neural net to detect water. We got a much better result. Right, and again, you can start to track this stuff over time. So some water reservoirs have instruments that measure what the level is. And we can use that for backtesting and for benchmarking. So this plot right here, the blue curve is what we measured, and the red and the green curve are basically the ground truth for that particular reservoir. This plot is showing for another reservoir. Again, the blue curve is our curve, which looks reasonable. We don't know the ground truth for that reservoir. The green is showing Landsat. So there you can kind of see it just like drops to 0 randomly. It's a much noisier signal. All right, so hopefully that kind of gives you an idea of what we're doing and why we're doing it. So I wanted to spend some time talking about satellite imagery. My background prior to Orbital Insight was just kind of traditional computer vision. I was doing like bananas and cats and stuff in internet images. So a lot of this stuff was new to me, and basically want to talk about what I thought was interesting or what I learned. All right, so what are the different properties? What do satellite images look like? Let me see, you can kind of see it. So one interesting thing is there are different bands. And a band just means a range of wavelengths that the sensor is capturing. So the most common thing that you'll see is something called panchromatic. And that just means the sensor is capturing all visible light. And so what you get out of that is a grayscale image. You usually don't see these, right? If you go to like Google Earth or Google Maps, you'll see color images. So the second most common thing is RGB. And that's what we're all used to, most of us. But there's an interesting issue here, which is it turns out most of the time the RGB image will be lower resolution than the panchromatic image. And that again has to do with the physics of the sensor. So there's this really, really common operation called pan sharpening in the satellite imagery world, where you take the panchromatic image, which is high res, and you take the RGB image, which is low res, and you fuse them together somehow to produce a high res RGB image. And there's a lot of different algorithms for it. Some of them are pretty straightforward. But if you ever play around with satellite imagery, like if you go to Landsat or something, just FYI, if you just naively grab the RGB, it's going to be lower resolution than it could be. Some other interesting bands, there's thermal bands and there's infrared bands, and they'll break these up into different ranges. Another really common thing is something called NDVI, which is a vegetation index. It's a formula to combine the red and infrared, one of the infrared bands. And the formula is based on the wavelengths that chlorophyll absorbs. And so what happens is green vegetation will pop out in this band. And a lot of times people will kind of create a false color image where they'll swap the red channel with the NDVI. So if you ever see these funny kind of images where fields appear in red, that's what that is. It's most likely NDVI. So it's used a lot for agriculture. A couple other things, pre-processing. So these are things that are typically done by the satellite image provider. So one very common thing is orthorectification. So again, I mentioned some of the satellites will move their camera, and if you take a picture at an angle, you're going to have perspective distortion. And you can usually get imagery that's been orthorectified for you, and they use a digital elevation map to do that properly. Basically removes the perspective distortion. So if you draw a perfect square on the ground and you take a picture at an angle, it might look like a trapezoid or something. But once it's orthorectified, it'll be a square again. And then the other thing is atmospheric compensation or correction. So they'll try to remove the effects of haze, fog, smog, that kind of thing. All right, and then the other big one, I've talked about this a little bit already, but different resolution, right? And again, there's this trade-off between the temporal frequency and the spatial resolution, usually. All right, so what are some nice things about satellite images? Well, one nice thing is there are a lot of knowns. It's kind of a constrained problem. So you know the resolution, you know the viewpoint, you know the sun angles, like I mentioned, so you know which way the shadows will fall. If you really need it, you can get the sensor metadata, so you can actually get the wavelengths for each band. And the imagery is geo-referenced and it's registered. So the images are aligned. They're not pixel perfect. They'll be off by like 1 or 2 pixels, but it's pretty good. The other thing that I found kind of interesting is that, again, coming from a more traditional computer vision background, you don't need much scale invariance. And what I mean there is when an object moves closer to a camera, it appears larger in the image, right? So let's say you're like building a face detector for a point-and-shoot camera. You really have to think about that because the face could be tiny or it could fill up the entire image. And with satellite imagery, you don't really have that issue. These things are so far away, the camera's so far away that things moving off the ground a few feet doesn't matter. The only time that it matters is that some objects are just naturally vary in size. And so in those situations, and I'll show an example later, you might need to worry about this a little bit. What are some challenges? So the obvious one is clouds, or I don't know if it's obvious, but once you see it, it's obvious. When there are clouds, you can't see anything on the ground. There are some technologies like synthetic aperture radar. It's an active sensor, so it can actually see through clouds. But regular optical imagery, you won't be able to see anything. And that's really important because if we're trying to count cars and like look at trends of cars in parking lots, we feed in a cloudy image into a car detector and it says there are no cars. And that messes with all the statistics, right? So that's really important for us to find the cases where there are clouds and take them out. Then there's like typical things like lighting changes, atmospheric changes, and I'll show an example in a second. You can have haze, fog, kind of a gradual spectrum between clouds and clear. And then there are viewpoint changes. So I did say that the imagery was orthorectified, so you might think like, why does the viewpoint change? Why does the viewpoint matter if it's been corrected for that? But it does. So here's an example. It's the same set of buildings, same spot on Earth, but the sun angle is changing and the viewpoint is changing. So the registration and the orthorectification means the bottoms of the buildings will be in the same spot, but you can't correct for the fact that the satellite saw a particular side of the building. And so you get these kind of awkward looking images because it feels like it should be like you're looking straight down, but you're not, and so you see sides of buildings. And you also see shadows falling into in different directions. So if you wanted to do something like change detection and you just kind of naively took pixel differences, obviously it wouldn't work, right? You'd get a bunch of differences all over the place, even though nothing is changing in this case. All right, so another huge issue for us is resolution. And this is kind of funny. When I was in grad school, my PhD advisor was teaching an image processing class, and I think he was talking about corner detection, and he was talking about sub-pixel accuracy for corner detection. And I forget if this is his line or he was quoting someone, but he said something like, the pixel is dead now, right? Because cameras are like 8 megapixels, 13 megapixels. When you have thousands of pixels across, talking about sub-pixel resolution is kind of silly, right? I mean, almost always, whatever your input image is, you downsample it first, right? You throw away the extra resolution. That's not the case in satellite imagery. So this is a car. This is 50 centimeter imagery. That's what a car looks like. Very hard to tell what it is unless you look at more context. And again, these things, I mean, the fact that you can see this from space is crazy, like it's so far away. And just to drive the point home, like this is what a car looks like in a typical computer vision data set, right? It's just a completely different situation. And it has its own challenges because the viewpoint changes a lot more. You can look at the side of the car. We're mostly looking from the top. But resolution is a big deal because a lot of times we're trying to find things that are very small. Yeah, so that kind of concludes my spiel about satellite imagery. If you want to play around with satellite imagery, again, there's this program that the USGS runs called Landsat, and it's actually freely available. It's on AWS. They host it, and then built in the last year. And I'm not going to go into like all the details like I did in the beginning, talking about like the whys, but this is just to give you a sense of the types of problems that we work on. So cars we already talked about. So we detect cars. This is a large vehicle detector, so it'll fire on buses, trucks, larger vehicles. The blue stuff that you see is we're masking out anything that's not a road. It helps clean up some of the false positives. This is an airplane detector. So this is a situation where the object just naturally comes in various sizes. It's never going to like fill the entire image, right? So you know what the size range is, but you do have to worry about scale in this particular case. This is a residential house detector. So if you want to look at a community, this is in Phoenix. If you want to look at a community that's being constructed, you can track the rate of construction, like how quickly are they completing houses. You can do something like that. This is a more coarse building detector, so it's just labeling every pixel as building or not building. So this is useful if you want to get broad statistics over a large area, like how much of it is covered by buildings. So sometimes you don't want to just count the number of buildings. You actually want to know the building volume. And the reason why you might want to know that is if you're interested in things like steel or concrete, right? So a big building means something different than a small building. And so I think the most obvious, like again, coming from a computer vision perspective, the most obvious way to do that is stereo, right? And some satellites will take stereo pairs. They'll take 2 pictures with a few seconds in between. But not all of them do. And so another way of getting at an estimate of the building volume is to look at shadows. So again, we know where the sun is, and if we can detect and count the shadow pixels in the image, we can get an estimate for the actual building volume. This is land use. So this is classifying every pixel into one of several categories. So things like water, urban, barren, forest, and so on. So the middle column is the national land cover data set. And on the right, this is like hot off the press. This is our ConvNet results that we're getting right now. Okay, and the last one is clouds. I've already talked about why it's important. So for this one, we didn't build it to be per pixel labels. So it just kind of, at a coarser level, chunks the image up into little squares and says, yes, there's clouds in here, or no, this is clear. All right, so what are the patterns there? One thing is most of the problems that we work on are essentially detection and semantic segmentation. Right, so we want to label every pixel in the image as something. Occasionally, we'll run into image classification type problems. This is closer to what you see in things like ImageNet, but those are less frequent. And the other thing is, hopefully what I got across with that is we work on a lot of different problems. And if you were to go and for every new problem, you got 2 engineers and they started developing things from scratch, like a brand new image processing algorithm, it would take forever. You wouldn't be able to scale. Then you might say, well, you know, what about machine learning? We can train a random forest or an SVM. And that helps because that kind of helps you generalize to new domains a little bit quicker. But what happens is you still spend a lot of time doing feature engineering. right? So hog might work well for buildings, but maybe for land use you need textons, but then cars are really small, so none of those things work, and you have to do some Gabor filter thing. And that was like a bulk of my PhD, right? And that's one of the reasons why deep learning is such a big deal right now, because it removes that step. So the whole thing is trainable. You feed in kind of your data in its rawest form, and internally it's learning this hierarchical representation. So it's doing the feature learning, the feature engineering for you, and it's actually doing it better, right? So you get better results. And this has been happening across the board in like every domain. One last thing I was going to say. I've been kind of surprised. I was kind of skeptical in the beginning, honestly. But I've been consistently surprised with how well it works and how robust it is. And we have data sets that some are large and some are small. One thing that you sometimes hear people say is that, oh, well, to use deep learning, you need a giant data set. I actually don't think that that's true. I think you can get pretty good performance with moderately sized data sets. This is just to show you an example. So this is from 2012. This is a paper about cloud detection. And you can see the algorithms they baked in a ton of domain knowledge about the particular object, in this case clouds, and they made a bunch of assumptions about what the input was. So in this case, it was specifically for Landsat. Landsat happens to have a ton of different bands that a lot of other satellites don't. And in our case, as I mentioned, clouds are a big deal for us across. Another way to think about that is that you kind of encode the image into some representation that has everything that you need in there, and then you learn how to kind of decode it back out into the label map. One thing that a lot of people ask us, and kind of comes up a lot, is, do you guys fine-tune from an ImageNet model? And this is really interesting. This is a really common technique. If you read a paper from some computer vision conference about convolutional nets, almost surely they'll say we fine-tune from VGG or whatever else from ImageNet. And there's some issues with this. So one issue is, which layer do you copy? Do you copy all of them? Do you copy only the bottom couple? Or how do you make that decision? And the other question is, how similar does my task have to be to ImageNet for this to make sense or to work? And I don't think there's a great answer for this. There's a nice paper on the topic where they did a nice empirical study about this. But the intuition, I mean, I guess it kind of makes sense. The bottom layers are really generic. You'll almost always, if you're training on some kind of imagery, you'll see Gabor-like things. And so those ones you can transfer over. And as you get higher and higher in the layers, you get more and more specific to that task, right? But in terms of like a recipe for how exactly to do this, I'm not sure if we have that yet. I think it just kind of boils down to you try a few different things and see what works. But there are more issues for us. So the bigger issue for us is that if you fine-tune from ImageNet, from one of the ImageNet models, it restricts the network architecture, right? And in particular, with ImageNet, usually, for example, the receptive field is something like 200 by 200 pixels, which is pretty large. The output is subsampled by a factor of 32. So you really got to do one of those tricks to expand them back out. And then the other interesting thing is the input is an RGB image, which again makes sense in most applications. But for us, sometimes we have infrared, sometimes we have thermal, and we want to use that. It has a lot of information there. And it's not clear how you would fine-tune from ImageNet, but then also feed in these new inputs. Let me just go back. So kind of the takeaway message there is we've actually been successful in not fine-tuning from ImageNet. I'm going to skip, well, maybe I'll fly through this since I'm running out of time. Just like kind of a laundry list of various tricks, I shouldn't call them tricks, techniques that people have published recently that are interesting. Different solvers. I get different results. So for some applications, one solver works well, and for another application, another solver works well. I think Nestrov is kind of the most consistent. It's kind of like the go-to thing. Batch norm, for us, so far what we've seen, it doesn't seem to hurt, at least in terms of accuracy, and sometimes it helps, which I think is pretty consistent with what other people are saying. I'll skip the LCV initialization thing. Dilated kernels is kind of an interesting one. It lets you have a large receptive field without having too many parameters. So one way to think about it is having a convolutional layer with a large filter, a large kernel, but you kind of pin some of the weights to 0. They give a better explanation in the paper. All right, so I'll spend the last few minutes talking about some practical things. These are kind of like software engineering things that we found to be really helpful at Orbital. So you guys saw, like, we work on a bunch of different applications, and for each application, we get new data all the time, so we're expanding our data sets. And if you're not careful, you end up with a code base where you have like train car detector and then train other car detector with this other architecture. You end up with just kind of this unwieldy set of scripts, and they're all kind of long and complicated. So we've spent a lot of time thinking about how to make this more modular, how to make this more plug and play. And so we'll usually try to have scripts where you can just plug in a data set just by name, plug in different model parameters. So if you want to run an experiment where you fix the data set and you try different architectures, or you fix an architecture and you try different data sets, different variations of a data set, you can do that really easily. And this really helps us iterate quickly. So I'm just going to go through this example. It's kind of a simplified version of something that you might find in our code base. So let's say you want to have a script that will train a neural net and maybe benchmark it also. So the first parameter might be the data set name. And so we have this really simple API so that data sets of a similar type will have a consistent format and a consistent API. And so some pseudocode in Python, this is what it might look like inside the script. You have the name, you give it to this class, and it knows exactly what to do. Right? The data sets, we have a convention of kind of how we package them up and how we put them. We use S3, AWS S3. And the Python code knows exactly what to do. So none of this is specific to like car detection anymore. It's generic. One interesting thing is train and test splits. Everything is consistent, so that you want things to be reproducible, right? And then you have model parameters, and this could be a whole slew of different things. There's the ConvNet architecture, and we've tried to kind of package all of this stuff up neatly. The solver parameters, the initialization, fine-tuning weights, how you're doing the data augmentation, the random seed. I always recommend people to use set a random seed instead of like using the timestamp. It makes it a lot easier to reproduce the results later. And you might also have some things for evaluation for like, what kind of visualization do you want? What kind of benchmark do you want to calculate? And then the last thing is what we call like a package name. So what happens is when you finish training your classifier, obviously you have the weights. Like that's the main byproduct. Right? But if you've worked with Caffe, there's a bunch of other files. There's like this proto and the that proto and the deploy and the solver you want to keep, again, for reproducibility. And so what we do is we package all of this stuff up into one tarball, and we upload it to S3. And it has things like pre-processing and post-processing parameters, right? Because you might do certain things in pre-processing, post-processing. So we package all of that up together, and we actually, for reproducibility and for debugging, we actually include kind of all the stuff that went into building that model, which data set it was, the solver parameters I talked about, but even like the git hash of Caffe. Because these libraries are evolving quickly, and so if you use something 2 months ago, it might be completely different now. So this makes it really easy to both deploy and to also just kind of play around. If you open a Python notebook and you want to try running a car detector that you trained 2 months ago, you don't have to go like looking around in your code base for how to do this. It's really easy. We have a function that takes the name of the model, and it has everything in there that it needs. It knows how to unpackage it. And turn it into a detector object, and then you just feed in an image, and it spits out the results. One other question that probably like the most common question I get is, what libraries do you use? Do you use Caffe? Do you use Theano? Do you use TensorFlow? And it's pretty crazy. So this is a tweet that I found saying that in 2015, every 22 days, a new deep learning toolkit is released. And I don't know if they count like updates for the same toolkit or literally, different toolkits. But either way, if you've looked into the stuff, it's overwhelming. There's a new thing, it feels like, every week. So here's my position on this. I think the dust hasn't settled yet. I think that whatever the landscape looks like now, 2 years from now, 3 years from now, it's gonna look different. So my main recommendation is, for now, try to abstract, like when you're designing the software, try to abstract your choice of the deep learning library as best as you can. All right, because most likely, even if you stick with the same one, they're probably going to change the API, or someone's going to publish a paper and it's going to completely change like how we model these things. So it's a good idea to be modular and to abstract this stuff away. In our case, because I don't want to avoid the question, so in our case, we use a combination of Caffe for certain applications and Theano with a Keras wrapper for other things. All right, I think that's all I had. So I'm happy to take questions. Thanks again for inviting me, and thanks to WePro for hosting.
So we have a am I live here? I'm gonna talk to the audio guy. So we is this coming through at all? Nope. How's that? Any better? Yeah. Any better here? Okay, now it's coming through, right? Okay, so sorry about that. We have a few minutes for questions and answers, and we'll pass these mics around, which apparently now work again. So everybody, when you take the mic and you ask a question, please stand up and speak into the mic so that our viewers at home can hear your question. And also, please introduce yourself. So give us your name, and if you have any kind of, you're from a particular company or affiliation or whatever, maybe that's nice to mention too.
Much. My name's Ken. I work for Dell. I'm interested in globally, like how do you look at environmental things, like temperatures around the globe and things like that, and what do you do with that kind of data other than jump up and down and scream?
Yeah, so I think part of the answer is we're usually partnering with someone, or we have a customer in mind that wants a certain kind of data. Right, and so you kind of start there. So one example is, like in that domain, we have a project where we're working on deforestation with WRI. So they want to know, obviously, where trees are getting chopped down, and they want to understand when people do cut down a portion of a forest, what does it turn into? Does it turn into buildings? Does it turn into some other kind of agriculture? In terms of, I think you asked about temperature. It depends on what we're doing. So for agriculture, if you're doing anything with agriculture, you're probably going to use some kind of weather data. I don't know if that answers your question.
Sure.
All right, did my best.
Yeah.
Hi, my name is Oscar. I'm working on a startup idea. And 3 of the things that I need for my prototype would be speed, embedded, and real time. So do you have any recommendations for a deep learning software for that, or other?
I think I'd recommend checking out TensorFlow. Just kind of be wary. It's a young library, so it's still changing a lot. But from my understanding, that's kind of what they were going for. They wanted to make sure that it can run on a phone, and it has both Python and C++ APIs. So if you want to run it on a device, I don't know about embedded, but I would guess that's your best bet.
What's it called again?
TensorFlow. So it's a Google run project. So that's one nice thing about TensorFlow is Google's throwing a ton of engineers at this problem.
Hi, my name is Ruchit, and I'm founder CEO of a company called Harvesting. I would love to learn your experience handling NDVI, and how do you deal with that with various reflectance and sunlight, because NDVI would be pretty complex to do at that time.
Yeah, so I'll be completely honest. I personally haven't played around with NDVI too much. If you want to talk afterwards, we have some more folks from our company. Glenn, one of our data scientists, might know a little bit more. I know we've done some work with agriculture, but personally I don't know too much about NDVI.
So you talked about, okay, my name is Oro, and I'm working on an idea as well. You talked about scale invariance. I was wondering how you accounted that into your ConvNet in terms of the number of layers, or what did you do to account for that one little constraint or one little benefit you had?
Yeah, there's a bunch of different ways that people are doing it. It's basically the problem is multi-scale object detection. And if you look around the way people are approaching it nowadays with ConvNets, one really popular approach is to do some kind of region proposal. So that's historically it's been kind of like some heuristic kind of hacky algorithm that at the end of the day spits out a bunch of bounding boxes, and they'll be different sizes. And then usually what people do is they crop those patches out and they reshape them to some canonical size, like 220 by 220 or whatever. And then they feed it into the ConvNet, and the ConvNet says, yes, that's the thing that you're looking for, or no. And then you aggregate the results. So that's one approach. And nowadays, the region proposal things are also convolution neural net based, so it's kind of a little bit nicer. So it's either that, or you kind of do the traditional Viola-Jones thing, where you build an image pyramid, and you run your ConvNet, which the ConvNet only knows about one scale, but you shrink the image more and more, or you expand the image, and you run the ConvNet on all those scales and aggregate the results.
Hi, Boris. John Jordan, and I had a question. You're obviously working with large data sets with a lot of objects in them, and can you talk about what you're doing with regard to annotation of data sets for training and verification, and whether you're doing anything to facilitate annotation and verification?
Yeah, that's a huge issue for us, and it kind of has multiple levels. So first off, obviously, we have some tools, internal tools. I'm really surprised that there's not really a great open source kind of platform for this. But just if you want to collect ground truth data for a computer vision module, whether it's bounding boxes or whether it's like you want to drop polygons, or you're doing semantic segmentation. There was Label Me, which was kind of popular for a time. I don't know if it's still popular. But we have an internal system, and like for us, some of the problems, you really have, somebody want to pick that up? Some of our problems, like you have to know that you're working with satellite imagery. It's kind of specific and niche to our use cases. And yeah, we'll usually outsource that somehow to get the labeling done. But it is a big issue because you do need training data, both for training and for benchmarking. The other thing I wanted to say was at the application level, like at the problem level, like let's say we're doing oil or something else, there's the performance of the computer vision module, which is just one piece. And then there's kind of the whole system as a whole with all the data science and all the statistical modeling. So like figuring out how to correctly do back testing. And that also goes into like how do you convince the customer that what we're doing is revealing some truth, right? Because in a lot of cases what we're doing, there is not really a good counterpart that we can compare to. So I don't think there's an easy answer for that. It kind of depends on the domain and the application.
Hi, my name is Sujata. I have a question on, have you looked into oceans and waves and see how waves change in oceans?
Oceans and waves, that's an interesting one. So most satellite providers that I can think of, they'll actually turn off the satellite. They don't take pictures of the ocean. So if you go to like Google Maps or Google Earth, and you look at the ocean, you're not going to see images there. And I don't know, maybe they do this because of power, maybe they do it because no one's interested in those images. But yeah, so for that reason, we haven't done much with oceans and waves.
Okay, let's thank our speaker again.
Thank you.
Thank you, Boris. At some point, we'll have some kind of a deep learning group coffee mug or something we can give the speakers at the end. But for the moment, that concludes our talk. But we have the space for another 45 minutes or so from our sponsors, and I'd really like to encourage everybody to hop up and move around and meet folks. And some of the questions you heard give you an idea of the kinds of people who are here with you. So take a moment to introduce yourself and meet somebody new. Okay, that's it for now.